In this video, we're going to take a look at some of the trig functions and their integrals, as well as take a few examples of some more difficult problems. And so one of the things that I wanted to do was kind of point out the relationship among the sines and cosines, and that is if you have sine, so if you have, let's say, f of x is equal to sine of x, then the derivative, that first derivative, is equal to cosine. That second derivative is equal to the first derivative of the first derivative, which is negative sine x. And then the third derivative of x is negative cosine of x. And then, of course, if we take the fourth derivative, then we come right back to sine. And so it's cyclical like that. And so are the integrals. Now we take a look at where sine x is, and then we go one up from there. So if we wanted to find the integral, or the original function, then we would take the integral of sine of x dx, and we would find out that if we do that, then we kind of bump up to this next one. It's negative cosine. Oh, we already did the dx, doofball, plus you need the x anyway. Negative cosine x, but we have to add that plus c in there. Okay, and for the other one, for cosine x, we notice that if we take cosine and we go up 1, we get to sine. And so f of x would equal the integral of cosine of x dx, and that would equal sine of x. But that would also have to have a constant on the end of it because it's an indefinite integral. When we get to definite integrals, that will go away, but we got to keep that for right now. Now, secant tangent, if you don't recall this, and there is no real good product rule and quotient rule for integrals, it doesn't quite work that way. And that's kind of a sticky situation, and so we save that for quite a while, really, to get some other techniques down. But we have to kind of recognize what this is, and the derivative of what is secant tangent, and it's secant. And so since the derivative of secant is secant tangent, then the integral of secant tangent must be secant plus c. Same goes for negative cosecant cotangent. We have that is going to be cosecant's derivative, and so therefore if we integrate and take a look at the original function, integrating over negative cosecant x cotangent x dx, that antiderivative would give us cosecant x plus c. Okay, now for these final two, and this one is missing a negative sign. Now we could have done it without the negative sign missing, but I'm going to save that till later. So if we wanted to find out whose derivative was secant or negative cosecant squared, then we just have to kind of look through our derivative tables, and we find out that that is in fact cotangent. So the integral of negative cosecant x, or cosecant squared x dx, is actually cotangent x plus c. And finally, secant squared x, well, the antiderivative of that is simply going to be tangent. Plus c. Okay, so these are the trigs. Sines go to cosines, cosines go to sines. Now you got to be careful about what your signs are, not signs being SIGNs, the negatives and the positives, but ultimately you're just looking for patterns in the derivatives. If you can find a derivative that you recognize, you can take its antiderivative and go back to something else that you know. And the check for this, of course, is take the derivative. See if you don't get the same thing back. If you don't, now you got to look for something else. It's kind of a guess and check. All right, now using those newfound skills and values, let's go ahead and take a look at some examples. And if you have not seen the video on the basic integration rules, please take a look at those, because those are going to be necessary for these here. All right, so now if we wanted to find the original function or the antiderivative of our given function here, then what we want to do is we want to go ahead and say f of x is equal to the integral of 3x to the fifth plus 2 minus sine of x dx. And when we do that, then we can break that up. This is the integral of 3x to the fifth dx plus the integral of 2 dx minus the integral of sine x dx. Once you do this, you can go ahead and bring this constant out if you want, or leave it in. It's up to you. But when I do this, the integral, the 3 will come out. The integral of x to the fifth, and I better do this here. Let me go ahead and bring that out. Plus, and then this is going to be 2 times the integral of 1 dx minus, and there's nothing to bring out of the sine. Oop, I don't want to run into my next one here. All right, so now all of these integrals are going to have a constant of integration. You don't have to put 3 constants of integration. All the constants are going to combine in the end. So finish your integrating, throw the plus c at the end. Okay, that might change later on in a different class, but for right now, that's the way we're going to leave it. All right, so the integral of x to the fifth is x to the sixth divided by 6 using our power rule. And then we have plus 2 times, now the integral of 1 dx. I didn't cover this specifically, but x in this case has an exponent of 0. And so integrating that is going to give us an exponent of 1 divided by 1 is going to give us just simply x. So again, what kind of a function gives us a constant for a slope? A linear function. And then of course we have minus. Now the integral of sine was negative cosine. Negative cosine of x. After all of that, we say plus c. And now you can clean this up just a little bit. You'll notice that the 3 cancels with the 6 to make 2, and then over here we have 2 negatives for positive. And unfortunately, I've run out of room. So over here in blue, I'm going to say f of x is equal to 1/2 x to the 6 plus 2x plus cosine x plus c. And the derivative of that would have given you our 3x to the fifth plus 2 minus sine of x. Okay. All right, let's go ahead and take a look at the next example then. Let's try to do this one in a little bit easier time here. All right, so now we take our integral. We're integrating over that, and so we're going to have 5 over x squared dx. Whoop, I don't want to do that yet. Plus the square root of x minus secant squared x dx. Okay, so now that we have our integral there, let's go ahead and set it up and break it up. Now, from this first one here, I can factor out a 5, and I need to rewrite x to x, or 1 over x squared to x to the negative 2. And so f of x is equal to 5 comes out, the integral of x to the negative 2 dx, and I can break that up, plus, and now I have the square root of x. That's x to the 1/2 power, so I'm going to integrate x to the 1/2 power dx. Minus, I need to integrate secant squared x dx. Okay, now that I have that, I need to increase the power. This is equal to 5. Now I need to increase the power by 1 and divide by that same new exponent. So if I increase negative 2 by 1, I get x to the negative 1 all over negative 1 plus. x to the 1/2 increased by 1 is 3/2. X to the 3, wow, that is an awful, awful 3. Let me just go ahead and fix that up just a little bit here. Divided by 3/2 minus the integral of secant squared is tangent x plus c. And now you can clean it up how you need. Okay, this is going to be a -5 on top. The x is going to be underneath. And plus, now this is going to be, now that we're dividing by 3/2, same as multiplying by 2/3, x to the 3/2 minus tangent of x plus c. Usually once I get into the 3/2 and that sort of thing, I don't use radicals. I just don't. It becomes a kind of a pain in the butt. And so this is our original function that gave us a derivative of 5 over x squared plus root of x minus secant squared. All right, one final one, and then I'll be done. Now, for this particular example, we don't know how to deal with this. Tangent squared is not something somebody whose derivative we know. And so when things like this happen and you don't find your derivative right off the bat, go back to your trig identities. And so if we do that, I only know like 3 or 4, and I derive the rest when I need to because I just don't remember them. But I do remember that cosine squared x, I usually work in thetas, but cosine squared x plus sine squared x is equal to 1. I do remember that. That is one of the few that I do remember. Okay, now I need tangent. I have sines. I need to divide by cosines. So if I divide by cosine squared x on both sides here, then I get 1 plus tangent squared x is equal to 1 over cosine squared, which is secant squared x. Okay, so now instead of writing it as tangent squared, I can write f as, or tangent squared plus 1, I can rewrite it as secant squared. And so when that happens, now I have the antiderivative is equal to the integral of s, or secant squared x dx, which we all know by now is just tangent of x plus c. And so the derivative of tangent is actually tangent squared plus 1. Huh. You take the derivative, the power on tangent goes up. Weird. So that's an example of how to use the trig identities. Again, if you don't recognize something, start looking for identities and looking for these and looking for combinations of these basic rules.